Hey there, let's take a look at this example. It says the figure shown in the region of integration for the integral. So there's an f of x, y, z function here that we don't know. It makes this generic. We're not going to evaluate it. What's important is to set up the triple integral. And so this particular triple integral looks like it's made so that we integrate with respect to y first from 0 to 1 minus x. So there's a y equals 0, 1 minus x. And y is equal to 0 is somewhere. It's the plane, the xz plane. And then z goes from 0 to 1 minus x squared. You can see that z is equal to 1 minus x squared portion here. And x goes from 0 to 1. So there's apparently after this, there's 5 more triple integrals that we can set up with different limits of integration. So let's take a look at a slight change in this. And I won't talk about this particular integral because it's already done, but as we start talking about the other integrals, hopefully you can figure out how this original integral was obtained. But let's figure out the dy dx dz combination. So if you have the dy dz dx combination, which is what we have here in this triple integral, you already know the y limits. So let's just rewrite the y limits here, and the y limits go from 0 to 1 minus x. Now the idea with the setting up limits for triple integrals is that once you have the first variable done, then you're left with an x and a z variable. And what we want to do is we want to look at the shadow this thing makes on the x and z plane. So it looks like it crosses here when x is equal to 1, and it crosses here when z is equal to 1. And then it looks like there's this parabolic curve. In fact, that parabolic curve is 1 minus x squared. So this is the piece that we're seeing here. Now, 1 minus x squared is the parabola that goes on forever there, but this is all we care about. And then the shadow that's being shaded in over here that we're concerned about is this space. So in figuring out the triple integral, once you have the first variable down, the x and the y variables will be dependent on only the two-dimensional shadow that we're looking at. Okay? At this point, we're interested in taking the integral with respect to x, and so I would draw a line parallel to the x-axis, and I would want to see where this region is going to go in, and that's going to go into this line, x is equal to 0, and then it's going to exit out of this piece of the parabola. Now that parabola is z is equal to 1 minus x squared. This is z equals, but I want an x equals parabola. So I would solve for x here. So subtract 1 and take the square root. Oh, I have to bring it over to the other side so that it's positive. So let me do this in 2 steps. X squared equals 1 minus z, and then take the square root. X is equal to, it's technically the positive and negative of this, but the negative would fall on the other side, which we don't care about. So we're just going to look at the positive part. So this is the positive square root of 1 minus z. So that is our set of limits for x. And then, oops, this should be z here. I put y, it should be z. And then as I integrate with respect to z, I have to acknowledge that they have to be constants. And it looks like it's just going to go from 0 to 1. So that's it. And now I have my integral in this particular order. integral, triple integral, the function, whatever that generic function is, with y first, dy, going from 0 to 1 minus x, then the x going from 0 to the square root of 1 minus z, and then the z going from 0 to 1. Okay, so that's two integrals now, the one that they gave us, and we found one, and so now let's try to find the others. For our next integral, let's do z, dz, and then maybe dx, dy. All right, now with respect to z first, I would have to draw a line parallel to the x-axis or parallel to the z-axis. And if I draw a line parallel to the z-axis, I would be going into this region. Z is equal to, that's just the xy plane, so let's call that z is equal to 0. Maybe I should do this in blue. So z is equal to 0 is my entry point. So my z limits first. Z is equal to 0. And then I will be inside of that region until I get out of that region at this z is equal to 1 minus x squared function. Okay, so that's the first part. I got two more parts to go, and the two parts is going to be dependent on the x and the y. So I would draw an xy plane, just two-dimensional, and I would try to figure out what this xy plane is over here. That looks like it's a line. It actually turns out to be this line over here. This is a line y is equal to 1 minus x. And this region that we're talking about here is this region over here. Okay, so if we are deciding to integrate with respect to x first, I would draw a line parallel to the x-axis, and I would figure out which way I'm going to go in and which way I'm going to get out. So our x limits will come in here at x equal to 0, and we'll exit at x is equal to whatever this line is. Well, this line is in terms of y, or y in terms of x, so let's just switch it so that it'll be x in terms of y. And so I have 1 minus y for my x limits. My last limits are constants, and that's the y, and that goes from 0 to 1. Okay, so let's set up the integral. It's going to be a triple integral. The function, again, is just a generic function, and we're deciding to integrate with respect to z first. Z goes from 0 to 1 minus x squared. Then with respect to x, going from 0 to 1 minus y. And then finally, with respect to y, going from 0 to 1. Okay? Now, let's do dz, dy, dx in that order. Because we have this figured out with respect to z first, we're going to use the same z limits over here. So that part is going to be easy. It's just the same. Now, we again are down to two variables, and it's going to be the same two variables, x and y, so we can reuse the same graph, the same two-dimensional graph. But this time, we're interested in integrating with respect to y first. So with respect to y first, I would draw a line parallel to the y-axis, and I would see what I enter in. I enter in at 0, and then I exit at this y function, 1 minus x. And then my outer limits are constants. We're going to go from 0 to 1, and so I am finished with this integral. So this is an integral of the function, and integrating with respect to z first, from 0 to 1 minus x squared, and then integrate with respect to y from 0 to 1 minus x, and then with respect to x from 0 to 1. Okay, so that part's done. Now the last two are actually going to be a lot more difficult, so I'm going to maybe I'll just do one of them, dx, and then maybe just dy and then dz. And we're going to see that we're going to run into a little bit of a problem here. And the tricky part is that it's hard to see it with this graph, but I redrew that graph using CalcPlot 3D. So this is the region that we're talking about here. And then the idea, well, let me show you what I did that's related to a couple of problems that we have already figured out. We could draw a line parallel to the z-axis, and then we can see it go in. If we draw that line, we're going to see it going into the region down at the bottom when z is equal to 0. And then it's going to be inside of the region until we get out at this graph over here, and then we're out of that graph. So we figured that out, and then we decided if we look at this flat, let me see if I can get it to look at it from on top. It's a little twisted. Let's actually see if I can get it in the right orientation. All right, maybe this is the best I can do. With respect to x and y in the xy plane, then you have this triangle. So that triangle is essentially this triangle over here. All right. So the other way we did this was to draw a line parallel to the y-axis. That's the stuff that they did. And then if we were to trace it through, we would be going into this region when y is equal to 0. And then we're going to be getting out through this plane, y is equal to x minus 1 or 1 minus x. And then look at this on an xz axis. It's that half of that parabola that we were talking about. Okay, so those are the ones that we did. They didn't have much of an issue. Now, the issue happens when we take the derivative. We're interested in integrating with respect to x first. And what we want to do is we want to draw a line that's parallel to the x-axis. Now, if we look at it flat, like the x-axis is directly pointing at you, you can see that there's two different regions that's going into. Let's look at the back. The back looks like it's a square, so this is where we're going to enter. So we're going to enter through this region. We're going to enter through this square in the region. And so it's going to go in here. But let's look at the front, or the top part. If you have the x, positive x going at you, you see that it gets out of this green graph, which is that curved graph, that z is equal to x squared graph. Okay, that's fine and good, except if I have another line. Now this is supposed to happen, that's good for either, whatever line we choose. But if I have a different line going into the region, I see that it would come out of a different graph. Okay, so this is not good for us. This particular setup is not good for us because it's coming out of two graphs. So let me get a couple of snapshots of this so I can write it out in our notes. And I have to talk about the issue that we have here. So the issue that we have is that when we integrate with respect to x first, we're going to essentially have two different things to worry about. We're going to come out of this graph over here, which is that z is equal to 1 minus x squared graph. And then this graph over here, which is y is equal to 1 minus x graph. And so if we try to set this up, we're going to need to have two integrals that we need to add together. Okay, not only that, if we look at that graph again and look at it so that we're looking at the yz part, it was right there. There we go. That's good enough. Looking at the yz part, when we figure out the limits for the x, we need to figure out the limits for the y. And what happens here is that in the two integrals that we're going to have, we're actually going to, your integral with respect to y and z is not just this box, but it's going to have to split up based on this curve over here. So this part of the curve is going to be different from this part of the curve. Okay, so we need to know where that curve happens or what that curve is. And it looks like it's the intersection between these two graphs. Now, how can we make them intersect? It looks like, let me write down these two functions over here. We have the function, well, it's already written over here, these two functions. And then I want it with a y and a z, so maybe I can solve for x here. X equals 1 minus y, and then I'll put that in here. Z is equal to 1 minus x squared, so that's 1 minus y squared. What is that? Let's simplify it a little bit. 1 minus, and then we have to FOIL this out, 1 minus 2y plus y squared. Let's see, the 1's would cancel, and the positive or negative becomes a positive, and then negative, and then positive becomes a negative. So this function here is that z is equal to 2y minus y squared. So we're going to have to split this up between two integrals. Okay. All right. So let's see if we could do that. We're still working with a dx, dy, dz combination. Now it looks like our first integral would be, if we're going to integrate with respect to x, we're going to enter through 0, and then we're going to exit through this x value of this graph. So this would be x is equal to, I think we already did this, 1 minus z under square root. Now, if you're along that graph, then you're looking at this green part over here. And if we're going to integrate with respect to y next, we need to find y limits. We need to find a line parallel to the y-axis, and we have to know where it goes in and where it goes out. So where it goes in is this graph right here. That's 0. And where it goes out is this. We have a little bit of a problem because we need to solve for y here. So how are we going to solve for y? I don't know. Let's try factoring a y out. Y minus 2 equals to z. Oh, you know what we can do is we can complete the square. Not the best thing to do, but let's see if we can complete the square. To make this a perfect square, I need to add 1 so that this becomes a perfect square. Remember, this is a perfect square. So if we add 1 here, we need to subtract 1 here. So we add 1. Oh, we need to add 1. Add 1 to both sides. And then this is a perfect square. 1 minus y squared. And this is z plus 1. So if I continue to solve for y, let's take the square root of both sides, plus or minus. I'm going to put plus or minus here because I'm not sure which way to go yet. And then let's bring this y over to the other side. So this is equal to 1 plus or minus or plus, it doesn't matter. Z minus 1. Now, we have to choose which one it is, the positive or the negative side. And I think this graph would continue down here because the y's intersect at 0 and 2. So this is 2 right here, 0 and 2. And so if we look at that, this is the positive part right here, positive part of the square root. This must be the negative part of the square root. So it must be y is equal to 1 minus the square root of z minus 1. So that is the exit part. 1 minus square root of z minus 1, or z plus 1. That's a plus. And then our z limits are constants. Z going from 0 to 1. Now that's just one part of the integral. We still have this blue part of the integral that we need to worry about. And so the blue part of the integral says that our x is going to go from 0 to this graph. So we need to solve for x. That's 1 minus y. And then now two-dimensional, we're going to look at this graph over here. So with respect to y, draw a line parallel to the y-axis. This time I'm going to go in this function that we found. This is going to be my lower function, z plus 1. 1 minus the square root of z plus 1. And then we're going to exit this y equals to 1. And then our x or our z limits is left. So that's just 0 to 1 again because it has to be constant. So if you were to do this dx, dy, dz, you would need to do two integrals. We have the function dx. X goes from 0 to the square root of z, or 1 minus z. And then dy goes from 0 to this function, 1 minus the square root of z plus 1. And then dz goes from 0 to 1. Now that's only going to give you a piece of the volume, so you need to add another triple integral. This time it goes from dx dy, or f of x, y, z. Dx goes from 0 to 1 minus y. The y, this time this is the lower limit, 1 minus the square root of z plus 1. And then the top limit is 1 for the y, and then dz goes from 0 to 1. Okay, so this is your not very nice looking integral. So there's one more left that we're not going to do. I'm not going to do it. Also do dx, dz, dy, and that is going to be just as difficult. Well, we got the x part already down. You just have to rewrite your two-dimensional y-z plane so that you're integrating with respect to z first. But in both of these cases, it's clear that this is a lot more difficult to set up because you have to do two different integrals. So clearly, one of these first four integrals would be easier to compute, depending on what the function might be. And so you have to be kind of selective as to how you integrate, which one you integrate with respect to first, etc. Okay, so hopefully this gives you some idea of approaching these integrals, these triple integrals, and trying to find the limits of integration by looking at the solids. All right, good luck.